Hi everyone. This video is about thinking about functions as vector spaces and where the idea comes from and why we would want to do that. So when we learn linear algebra the first time, it kind of seems like a subject that has interesting ideas but no applications because of the length of the class that you usually get introduced to it in. And in a combination linear algebra differential equations course, it's even a shorter introduction than you would get in a first course in linear. So what I want to do is talk about why we want to take this perspective and how it is that it is so useful. So what I want to do is I want to walk through the analogy with finite dimensional linear algebra and how we bring that forward into thinking about spaces of functions and what we can do with those ideas once we get there. So we're going to start by reminding ourselves of some of the basic ideas of finite dimensional linear algebra, which everyone probably has seen in pieces, but maybe not as a complete picture, and particularly not maybe with an application of why you would want to use those things. So the first thing I want to talk about is R3. So let's think about R3. So this is just regular old Euclidean finite dimensional linear algebra. So vectors in R3 look like A, B, C, by which we mean A times the vector E1 plus B times the vector E2 plus C times the vector E3, where E1, E2, and E3 are called the standard basis vectors. E1, E2, E3 are the standard basis. And A, B, and C are called the coordinates. So what the coordinates do is they tell you the particular way that you can combine E1, E2, and E3 together in order to get the vector ABC out the other side. Now, inside R3, we could find smaller spaces of vectors that live inside. And what do I mean by that? Well, in three-dimensional space, you have lines and you have planes, and those are both considered to be linear spaces. And what I mean by that is, if I take linear combinations of any vectors that live in a line, I stay inside the line. And if I take linear combinations of any two vectors that live inside of a plane, I stay inside the plane. So what is a linear combination? A linear combination of vectors, say v1 through vn, is just a sum where I take constant c1 and I multiply them by the vectors v. c1 through cn are just some constants in the real numbers. Of course, these could be complex numbers, and they will be when we get to the second part of the course about Fourier analysis. But for now, we can just think about linear combinations as real linear combinations. The basic idea is that if I start with the vectors, I can multiply them all by scalars, and I get a new vector out. And the set of all possible linear combinations of a starting set of vectors is called the span of those vectors. So if you started with, say, just v1 and v2 as vectors in R3, then the span of v1 and v2 is just the set of all possible combinations of v1 and v2. If v1 and v2 are linearly independent, this set will be a plane. So for example, the span of the vectors 1, 0, 0 and 0, 0, 1 in R3 is a plane. And usually the way we visualize this is we think of, here's R3, and that if we have the vector 1, 0, 0 and the vector 0, 0, 1, then the combination of those two vectors spans a plane. Two vectors that are linearly independent span a plane. Now, if the vectors I'm given are orthogonal to each other, so say that I've got v1 and v2 that are orthogonal. And what I mean by orthogonal is that v1 dot v2 is 0. Then I can form a closed linear subspace just the same as before, but with an extra property. So form the span of v1 and v2, which again, remember, is the linear combinations of v1 and v2. So far I've said nothing different. So we call this a closed subspace, because if I took two vectors inside the span and I add them, I stay in the span. If x and w are in the span of v1 and v2, then so is x plus w. And so is any scalar combination. So that's what we mean by closed. And the fact that they're subspace, there's a secret word we're missing here, which is linear. So a closed linear subspace is a set where if I take any linear combinations of things in the set, I stay in the set. Subspaces are great. And they're great because they're sort of like self-contained universes of vectors within a larger vector space. So if you had three-dimensional space, and inside of it you have some plane that cuts through, defined by two vectors, well, this plane is sort of self-contained. It follows the same geometry that the big space does, but it's like a micro-universe living inside of it. So it's a two-dimensional space living inside of the three-dimensional world. Sometimes I might want to take a vector that does not live in that subspace and figure out the vector in the subspace that kind of represents it. So if I had a vector outside of a space and I wanted to say, okay, if it was in the space, what vector would it be? We call that projection. So if I have a vector v that is not in S, where S is equal to the span of v1 and v2, then I can project v onto S. And so the picture that I have in mind here is this. Here is my subspace S. And S is built out of perpendicular vectors v1 and v2. So those are at a right angle. That's what we mean by orthogonal. v1 is orthogonal to v2. And I have some vector poking out. Maybe we shouldn't call this v. Maybe we should call it w. So I've got w that is not part of that set. So I've got this w poking out. And I want to know, what is the vector in the subspace, in this plane, that represents w? So the plane here is supposed to represent the span of v1 and v2. Well, what we do is we sort of cast the shadow of w down onto the plane, and then we find this vector right here. So that vector is called the projection of w onto S. And it has a very nice computational formula as long as v1 and v2 are orthogonal to each other. So the projection onto S of the vector w is given by the dot product of w with v1 over v1 dot v1 times the vector v1 plus w dot v2 over v2 dot v2 times the vector v2. And what we can think here is what this really is it's telling you a c1 v1 and a c2 v2, where the c1 and the c2 are some coordinates. And that tells you that the projection is a linear combination of the v1 and the v2 with this really nice computational formula that we can use. Now, one of the really awesome properties of the projection onto a subspace is that it's the closest vector in the subspace to the original vector that you started with, in the sense that this distance right here, or you can think of it as the error between w and the space that you're mapping it onto, that distance is minimized by this idea. The projection of S onto w is the best, what's called least squares approximation of w inside the span of v1 and v2. And the reason we say least squares is because the distance formula in R3, or any Rn, is built out of taking the square root of a sum of squares. So what I mean is that the distance between W and the projection of W onto S is equal to the square root of the sum of Wi minus the ith component of the projection of S onto W. I guess I should have given that vector a name, squared. So least squares mean that the way that we're computing the error here is with this distance formula. I subtract the vectors, I square all the components, and I add them up. And what we're saying here is just this distance rate, the thing that we're computing is the length of that distance right there. So the error between W and the plane is just given by that length, and that length comes from this formula. Okay. I mean, that's a great geometric fact. We've got a least squares approximation, or we can think of it as the closest vector. Projection of W onto S is the closest vector in S to W. So if the only world I was allowed to live in was the plane S, then I could take every other vector in R3 and I could just project it down to S. And that would be, it's like looking at the shadows of what's happening in the big world, but it gives me a way to restrict my attention just to that plane. The first thing you might think is, why would you ever want to do that? Great, you can project things. That sounds wonderful. So what can I do with it? Well, the first idea here is that we can solve equations that don't actually have solutions using this idea. So where does this usually get seen? You see it anytime you're trying to fit a best fit line to data that does not meet the description of the line that you're trying to fit. So what do I mean by that? Well, if you had a situation, say, where you were trying to plot some points, say 0, 0, and I don't know, 1, 2, so let's put a dot right there, and let's say 2, 1. And you say, I want to put a line that goes through those 3 points. Well, obviously the answer is you can't. There is no line through these points. This can't be done. But maybe we can come up with the closest we can get. And so what we can do is we can look at the space of all possible lines and try to find one that misses all of the points in a way that minimizes how much the total miss is. So the idea here is that if I could draw a line through here, and then I had, say, there would be an error here, and an error here, and an error here, maybe what I can do is minimize the error that my line misses those points by. And it turns out to be the case that the correct way to do that is with linear algebra and projection onto a subspace. If you try to write down a system of equations that describe this, if you had some unknown function y is equal to mx plus b that you're saying, okay, I want to find a y equals mx plus b that runs through those points. Obviously that can't be done, but if it could be done, what equations would they need to satisfy? Well, I would need it to be the case that 0 was equal to 0m plus b, and I would need it to be the case that 2 was equal to 1m plus b, and I would need it to be the case that 1 is equal to 2m plus b. In linear algebraic terms, what you can do is you could rewrite this as a matrix equation, as the vector 0, 2, 1 times the matrix 0, 1, 1, 0, 2, 1 times the vector mb. So this is a setup that we usually call b is equal to ax. And this equation is inconsistent, which is exactly what we expect because there is no solution. There is no line that will go through those 3 points. So it's impossible that I can find a solution that does it. But what if instead of trying to find a solution, I try to find the projection of this problem onto the closest possible solution? How am I going to do that? Well, I look at all the possible lines that involve the parameter m and the parameter b, and and I just project my problem onto all possible lines. And I know that if I project, I'm automatically going to get the one that minimizes the error. So there's a formula for this. This is called least squares approximation. In MATLAB, this is easy to compute because you would just write x is equal to a divided by b, where this is matrix division, which of course doesn't make any sense because you can't actually divide matrices. But what this represents is if a problem is consistent and the system is square, then it writes x is equal to a inverse b, if that's possible. If that's not possible, it computes what is called a least square solution with this fancy formula. So use the least squares formula, which basically boils down to a transpose ax is equal to ab, a transpose b. And then once you have that, you can invert both sides, and you get x is equal to a transpose a inverse a transpose b. And this thing right here is called the least square solution. Now, it doesn't actually solve the problem, but it gets you a best fit line. So it's the closest you can come to solving the problem with the least amount of error. So if you want a picture of what that looks like, you can walk through the MATLAB demo that I've just built for this topic. So here, what I've done is I have defined a set of points, and that set of points is right here. So 0, 0, 1, 1, 2, 1, and 3, 3. Here's the scatter plot of those points. Obviously, there is no line that goes through those 4 points because they're not collinear. What I can do is the least squares property, or calculation on these, and what we're going to turn up with is, so if here you can see where I do a divided by b, and the a divided by b is what computes the polynomial that comes out the other side, that is the m and the b, and if you plot that, what you end up with is the best fit line. And yes, obviously it does not go through the points, but it comes close to going through all the points in a way that minimizes the y error. And where it comes from is vector projection. So we project our system onto the space of possible solutions, and that projection turns out to be the closest possible answer to our problem. And it doesn't look like it, but in a more detailed linear algebra class, what you could show is that these expressions right here are doing exactly what I just said. This is a computation of the projection of our system onto the space of possible solutions. Okay. So the point there is not that you're going to be computing least square solutions of finite dimensional vectors. It's to give you an idea of what the idea of projection is used for. So we're approximating our system with a solution that is actually a feasible solution. So x hat is an approximation for the best fit line, or best fit curve, restricted to lines. Now, if I restricted to other functions, I would get different answers. I could restrict to parabolas, or I could restrict to cubics. And in each case, I'm going to get a different answer until I get to the degree where all of a sudden I can find a function that goes through all those points. So if you calculate in the field of cubics, you can find a unique cubic that goes through 4 points. So the idea is if I restrict my subspace of functions to just lines, I can't find a solution that goes through all the curves, but I can come really close by projecting. Okay, so the upshot of that is, in finite dimensional linear algebra, what do we have? We have a space, say R3, for example. We have a subspace. In this case, we can say that our subspace was the span of a couple of vectors, v1, v2. If we know that v1.v2 is 0, then that means v1 is orthogonal to v2, and that means that the projection of any other vector w onto the span of v1 and v2 is v1.v1, is w.v1 over v1.v1, v1, plus w.v2 over v2.v2, v2. And this thing is called the least squares approximation to W in S. So what we'd like to do is we'd like to take that idea of geometry and move it to the realm of functions. And I want to set up why we might want to do that first. If we could do that with functions, it would mean that we would never have to work with all of a function, that we could just do an approximation of a given function in terms of nice functions. So maybe I don't want to work with e to the minus x squared. Maybe I want to work with polynomials instead. Well, I can do that if I have a regime for doing approximation. But I want to make sure that my approximation is as good as it can be. And so if I want to do that, I have to have some way of minimizing error. And the way that we're going to minimize error is exactly the way we did it in the finite dimensional case. We're going to do a projection of a function onto a subspace spanned by other functions. And the result is going to be the function in the subspace that's as close as possible to the function that we started with. In the case of Euclidean space, the first thing we did was set up the machinery that we needed to have geometry, that is angles between things, and length, right? And we did that in the case of R3 or Rn with the dot product. So the very first thing we need if we're going to assert that functions are a vector space that have geometry and length is some kind of version of the dot product to go with it. Suppose that what we really wanted was that the projection onto some space S for a function g, whatever that is, we want that to be the closest vector in S to g. And S is going to be the span of some nice set of functions. I would like that idea to still work if I'm thinking about functions. I want to get rid of nasty functions and replace them with linear combinations of nice ones. Okay. What machinery would I set up to do that? Well, the natural machinery that you would set up would be exactly the dot product that we've already defined. Let's let L2 of minus 1, 1 be the space of functions where the integral from minus 1 to 1 of f of x squared dx is bounded. Now, the reason that we might do that is because an integral is basically like a sum. So you should be thinking that this is about the same as saying that the sum over all of the x values between minus 1 and 1 of f of x squared is finite. Now, it's not exactly the same, of course, because this is indexed discretely and an integral works continuously over an interval, but that's the basic idea. And to me, that looks exactly the same as the definition of the length of a vector in finite dimensional vector space. In finite dimensional vector space, we have this. We know that the length of some vector v is equal to the square root of the sum of its components squared. And if I put a square root on this, it would look an awful lot like the length of a vector f. Okay? And so that's where this condition comes from. This is a condition that is exactly equivalent to the Euclidean distance in finite dimensional vector spaces. Now, another thing that we know in finite dimensional vector spaces is that if I knew the length of a vector squared, that I could write that as the dot product of the vector with itself. Knowing that, I'm going to define a dot product of functions to be, so I'd still like that property to be true. I'd like the length of f squared to be equal to the function f dotted with itself in this sense right here. And that's going to have to involve this integral. So I want that to be the integral from minus 1 to 1 of f of x squared dx. Why not just let that be the length? After all, if it's the case that in finite dimensions I can use the square root of the sum of the components squared, I should be able to add up the sum of the components squared in the infinite dimensional case as well. What that's going to do is it's going to give us a way of evaluating the dot product of other functions. So we can define f dot g to be equal to f of x g of x dx. And that dot product is consistent with the dot product that we have in finite dimensional Euclidean space. And we can define what it means for f and g to be perpendicular to each other just by saying, well, f and g are perpendicular whenever it's the case that f dot g is equal to 0, but under this definition of f dot g. Once we have a notion of geometry, then we get all the rest of it as well. The most important space is the space L2. And so, again, we think about these as the square integrable functions, or the set of functions f that have the property that the integral from -1 to 1 of f of x squared dx is finite. Now notice, there's no other conditions on functions in L2. In fact, horrible functions have the property that their integrals squared are finite. Discontinuous functions, for example, functions with lots of discontinuities, and with a modification of dx that I'm overwriting because we're not in a super upper division math class or graduate school, if you're careful about the way you define the integral, there are functions in here that have infinite discontinuities. So L2 contains really, really nasty functions. But what live inside L2 are the continuous functions and the continuously differentiable functions. So L2 contains the continuous functions and the differentiable functions and the continuously differentiable functions and the twice continuously differentiable functions all live inside of L2 as subspaces of it. So L2 has inside of it the continuous functions, sometimes called C0. And it has inside of it the continuously differentiable functions. And so on down the chain. Smaller and smaller spaces as you require more and more conditions. And probably the nicest family of functions that lives inside of here is the analytic functions. And living inside the analytic functions is the polynomials. So the polynomials live inside the analytic functions, which live inside any n times continuously differentiable space of functions, all the way up to the continuous functions, and living on top of that is the space L2. So L2 contains a lot of really important and useful families of functions, and the same inner product works on all of these spaces. In all of these spaces, because all of these down here, in the same way that a plane is a subspace of R3, all of these are subspaces of L2. And they're inner product spaces with the inner product f dot g is equal to the integral from -1 to 1 of f of x, g of x, dx. At least in the case we're looking at. The interval can change, but the theory is basically the same. So why does any of this matter? Well, the first thing we've got is we can project functions onto subspaces in L2 using the inner product formula that we had before. If I had some function g of x, and I wanted to project that function onto the span of, say, functions f1 to fn, where all of the fi's are orthogonal to all the fj's, then I could write down that the projection of g onto the span of f1 through fn is just the sum from I equals 1 to n of the inner product of g with each fi over fi dot fi times fi. It's the same formula as it was in the finite dimensional case. So the obvious question is, how is that useful? First off, how is that useful? Second, where am I going to find families of functions f1 through fn that make this work? So the orthogonal families of functions turn out to be important specifically because they give us families that let us build these subspaces. If I know that I have a family of functions that is on the one hand orthogonal in L2, and on the other hand is also a basis for L2, then it means that I can always approximate any function inside of L2 with this projection formula. What does that get me? Well, what it gets me is that this vector right here, I don't know, maybe I'll call this g hat of x. That g hat of x is the closest function built by combining f1 through fn to the original function g of x. And close is pretty close. So why would you want to do that, and when is it useful? So the idea that I have now is if I can find a closest function, maybe I can use this to take functions that I don't really want to compute with and turn them into functions I do want to compute with. So the first thing we'll note is, so far what we've met is that the Legendre polynomials are an orthogonal family. Well, that seems like that makes them a good candidate for doing this kind of projection onto. And secondly, that not only are the Legendre polynomials an orthogonal family, they're also a basis for L2. So what do I mean? I mean that I can write any function in L2 down and I can approximate it with Legendre polynomials. So for example, suppose that I was doing probability and statistics and I had to deal with the most important function in probability and statistics, and yet one that does not have an integral that I can compute. E to the minus x squared. Let's make that our g. And I think I don't want to spend the time to do constant exponential evaluations. And I know that Taylor series don't work very well for numerical approximations, and so I'd really like to expand these in terms of functions that do work well for numerical approximations. Well, what I could do is I could replace g with a projection of g onto a subspace built out of Legendre polynomials. So let's suppose, just for the sake of argument, that I have a space S that is equal to the span of the Legendre polynomial starting at P0 and going up to, I don't know, P10. So what I'm saying is that S is a subspace built out of all of the possible functions that you can get doing linear combinations of P0 through P10. What I'm going to do is I'm going to project G onto S. The picture that I want you to have in mind here is just the same as before. This plane right here you can think of as being the span of P0 through P10. And living inside P0 through P10 are these vectors that are orthogonal to each other. So if this is P2 and this is P3, they're orthogonal. And so if I had some function g and I wanted to project it down onto the plane, well, the vector that I would get here is just the projection of g onto S. And the closest vector property still works. That's the vector inside of the span of those polynomials that is the closest we're going to get to g in the sense of least squares. And we compute it with the same formula. That is, we do the projection of g onto S, which I will call g hat, is going to be given by the sum from n equals 0 to 10 of the dot product of g and pn over the dot product of pn with itself times pn. Now, in practice, what are we producing here? This is a 10th degree polynomial. So I'm replacing, or trying to replace, e to the minus x squared with a 10th degree polynomial that represents it. The reason that you do that is because as soon as you're working in the land of polynomials, you can use all kinds of polynomial algorithms, and polynomial algorithms are way faster than working with abstract or symbolic functions when you're doing any kind of computation. And we know that this kind of approach minimizes the error across the board. It doesn't just minimize the error at one point. It tries to minimize the error everywhere in the same way that a best fit line minimizes the distance between each of the points and the line that runs through them. So if you do that, if you take the first 10 Legendre polynomials, and you project the function e to the minus x squared onto the span of those, what polynomial do you get out? And how good is the approximation you get? So in the MATLAB demo that I posted, I've actually given some sample code for this exact problem. You'll find that if you compute the function or graph the function e to the minus x squared between -1 and 1, there's no reason to restrict yourself to -1 to 1, but that's where we've been working, so that's what we do. That's a graph of the bell curve by itself. That function is in L2 because if you compute the integral, which is what this line does, then what you get is that a finite number, right? 1.0937 means that the L2 length of that function is bounded, so it's in L2. So we can use the projection formula to actually compute the expansion of the function e to the minus x squared in terms of Legendre polynomials. Now, I've suppressed the output here because a 10th degree polynomial with gigantic fraction coefficients is not a terribly nice object. But this plot that you're looking at right here, this plot, contains both the graph of e to the minus x squared and the graph of the approximation, which means that essentially we have a perfect approximation of e to the minus x squared in terms of polynomials. And replacing analytic functions with polynomials when we can do it is an outstanding way to improve computational efficiency. In fact, underneath it, that's what computers are really doing when they do numerical approximation, is they're breaking these things down into representations that they can work with. Another thing that we could do here would be to do the same idea, but now at functions that have worse properties. So what do I mean? Well, L2 contains all kinds of discontinuous functions. So piecewise defined functions, for example. So you could think of, in the example that I did in my demo on, the example that I did in the demo is to think about a square wave. So a square wave is just a function that looks like this. And the way that you define it is it's a piecewise function that you define in chunks that look like this. So you could write that g of x is equal to -1 when x happens to fall between -1 and -1/2. 1 between -1/2 and 0. -1 between 0 and 1/2. And 1 from 1/2 to 1. And you would get a graph out that went like this, where this is 0. This is 1/2, and this is -1/2. Now that function is pretty badly discontinuous, right? You've got all kinds of jump discontinuities. And working with discontinuous functions on continuous systems is actually pretty difficult. One application where this comes in is in circuit analysis, when you have, or any sort of analysis where you're trying to send particular kinds of signals into the physical system, whether it's chemical or computer or electrical. You send an impulse into the system to see how it responds. How will it vibrate? How will is there feedback in the system? So in order to work with this with the tools of calculus, which require continuous functions, what we can do is we can replace this function with an approximation. So maybe we could project g onto a subspace of, I don't know, Legendre polynomials. After all, if the square wave function g is in L2, I should still be able to use the projection formula on it. I should still be able to write down that g hat, which is the projection of g onto S, where S is equal to the span of P0 through P10, I should still be able to write down that this is the sum of g times pi over pi dot pi times pi. This is still valid. That formula still holds. The projection still works. I'm still taking g and projecting it onto the span of those polynomials. and it's the closest function inside the span of those polynomials to the original function. So the question is, well, does it work? Well, if you go to the demo, what you'll see is that when you're done doing that projection formula, so here's the square wave. So I've defined this as a piecewise function. It's bounded when you integrate. You get the square root of 2. And you can do an approximation. This is a 10-term approximation. This is the exact same thing I just wrote in the notebook. With a 10-term approximation, you end up with a continuous function that's already doing a pretty good job, right? I mean, it sees the jump from here to here and back down and back up again. So maybe what we just need is more terms to make the approximation better. So obviously it's not doing as well as it did in the case of e to the minus x squared, but that's a super smooth, nice function. So maybe we can do better if we just add more terms to the pile. Well, if you do that, what you'll end up with is this. Now that's a much better approximation. I mean, look how nice that is, right? The polynomial comes up here and it sees this and holds pretty tight to it, and then it leaps up and sees this and holds pretty tight to it, then back down and back up again. So maybe if I want a really sharp estimate, I could just let my subspace I'm projecting onto be like, I don't know, 100 polynomials, or even 20 of them. Well, look what happens if we go too far. So this is, in this particular problem, what we've done is we're projecting the square wave onto a set of 50 Legendre polynomials, or 51 Legendre polynomials, so P0 through P50. And if we do that, it doesn't look like we've actually gained very much in terms of how tight the function is at these interior jumps. And look what happens on the outside. I get this horrible oscillatory behavior out here where the function looks like it's running away to infinity. Now, theoretically, what's happening here is that you're still getting a really, really good least squares approximation to the square wave with the Legendre polynomials. It's just that what's happening on the outside is that the polynomial degrees are getting so high that you get these little skinny but ridiculously huge leaps up. Like, I think in this problem, you end up with approximations that have values as high as like 10 to the 13th. With 50 polynomials between -1 and 1. So the Legendre polynomials were an amazing basis for L2, for our vector space of functions, when we were looking at functions like e to the minus x squared. And I could build nice subspaces out of them and project them, and we got these great results. When I put the square wave in, I get a terrible approximation where the fact that polynomials can be unbounded turns out to be the case, or it turns out to be an operating condition in the quality of our result. So the question is, where should we go from here? Maybe we could find a basis of functions for L2 that it involves another property of the square wave. So the one thing that we didn't deal with this square wave is that it's periodic. So the square wave here is periodic. It goes down and up and down and up. It's a wave. And the Legendre polynomials, by virtue of the fact that they're polynomials, are not going to do well at the corners of these jump discontinuities. In fact, you always get this sort of ragged behavior at the corners, which is something called the Gibbs phenomenon, which we'll talk about more specifically when we do the next section of the class. The question that I want you to have in mind here is, okay, the Legendre polynomials were awesome for some types of functions that we got these great approximations. So maybe what we need to do is cook up another set of functions that are orthogonal to each other that we can consider as the basis for our subspace projection. Maybe we need more kinds of orthogonal basis functions. And it would be really awesome if we want to study periodic functions if our basis functions were periodic. And what it's going to turn out to be, I'm going to pull the curtain back a little bit here. What we're going to show all through the next portion of the course is that the machinery that we built in this section, inspired by the solutions to these famous differential equations and the idea of series, maybe what we can do is we can work with cosine and sine. And maybe if we build up cosines and sines of different frequencies, maybe that will be a basis of functions. And the first thing that I'll point out is it just happens to be the case that if you integrate this from -1 to 1 and n is not equal to m, this integral is 0. So there's your clue about where we're headed. All right. So this has been a technical video, but this is the glue that holds all of the ideas of the course together. The linear algebra is the language that we use not just to describe what we're doing when we find approximations for functions or when we're pulling them apart into their components, but it's also the language that gives us inspiration about where to look for formulas that we can use to make our computation and our approximation more practical and actually also more consequential as well. All right, so I hope you took the time to walk through this. This is not a required part of the course, but I think that what we talk about here is mandatory for understanding why we're doing it the way that we're doing. And after we get some Bessel functions and after we get some Fourier bases, I think it's going to be really obvious why we're doing it this way. All right, I'll talk to you guys later.